All right, so these three problems were pulled from the textbook. I can't remember which numbers they were, but it's asking you to provide an efficient synthesis for the following transformations. So before we start, what's the name of this starting alkyne on the left? It'd be butine, and then we need to number where the double bond, or in this case triple bond, originates. So what would it be? 1-butine, exactly. So we're going from an alkyne to an alcohol. We can't do that in one step, so there's got to be some sort of intermediates. I'm going to slide everything down here, and we can say, all right, well, what must these intermediates be? So we don't know how to make an alcohol directly from an alkyne. What do we know how to make an alcohol directly from? An alkene, right? So we could say, let's try to convert this alkyne into an alkene. And then can we change this alkene directly to this alcohol? Yeah, absolutely. So now let's fill in the missing reagents that we need. So for the alkyne to the alkene, meaning our first step, what reagent could we use? So we could use H2 and Lindlar's. Do we have to use this? Are we making a cis alkene? Oh, it's not cis or trans. So we could do either or. You could do the dissolving metal reduction. So it really doesn't matter in this example because we're not making one stereoisomer. It's not cis or trans, so you can pick either one. Can we use hydrogen and palladium? Yeah, if we did hydrogen and palladium catalyst, we'd go to an alkane, right? We would overshoot and we wouldn't stop at the alkene. So using one of these poison catalysts or dissolving metal reduction would be most appropriate. All right, in the next step, we want our alcohol to come off of this more substituted carbon. What reagent can we use for that? So acid and water would work well. Do we have to worry about rearrangements? No, not for this one. So you could use the oxymercuration, demercuration. However, most people would avoid it just because why use mercury if you don't have to? So I'd say this looks like a pretty good efficient synthesis for that first reaction. All right, let's do the second one now. Second one, we're going from an alkene to an aldehyde. Again, we don't have a good way of going directly from an alkene to an aldehyde. We have two different ways of making aldehydes, though. We can either do ozonolysis of alkenes, or we can do hydroboration oxidation of alkynes. In this example, do you think we're going to do ozonolysis? Meaning, can we just go directly to our final product by using O3 and DMS? Will that work? Why not? Yeah, we would lose one of our carbons, right? So we would make an aldehyde. It just would be a 3-carbon aldehyde. We want a 4-carbon aldehyde. So this won't work. So that means ozonolysis is probably off the table. However, we know that we can make an aldehyde from a corresponding alkyne. So in this case, it must be a 4-carbon alkyne. So maybe something that looks like this. And then the question is, well, what reagent would we need to accomplish that? I kind of gave a hint before with the name. It's one of our fancy new reagents. So I'll give you a hint. We're trying to do anti-Markovnikov hydration. So we can't just use acid and water at all. Yeah, hydroboration. We can't use borane, though. If you remember, we had to use the really bulky. Yeah, diacetyl borane or 9-BBN. So we'll try to be specific here. So really bulky borane, followed by sodium hydroxide and H2O2. So you could use that to convert your alkyne into an aldehyde. If you remember, it goes through an enol intermediate, and we'll actually talk about that tautomerization next week. All right, so now we're kind of stuck in this weird situation. We can't go directly from our alkene to our alkyne. We have to go through some other intermediates. So does anybody have a strategy? Give you a hint. We kind of did this on the pod. Bromination. So if you react this with bromine, right? You'll get anti-halogenation. You'll end up with the mixture of enantiomers here. However, it doesn't really matter because in the next step, you're destroying stereochemistry. And what's a good base to use if we're doing a double elimination reaction? Meaning 2 E2s. We need a really strong base. So normally what you'll see in the textbook is that sodium amide, NaNH2. And you'll see this in excess because you need to do this reaction twice, right? So 2 eliminations, one after another. And this is a terminal alkyne, which means we need to reprotonate it at the very end. So we would want to use water in that last step. So to me, this looks like the most efficient transformation for that. So, yeah, that's a good point. So let's go back in our notes really quick. So if you remember in this example, right, our first equivalent did our first elimination reaction, right? Then our second equivalent did our second elimination reaction, gave us the alkyne. But usually when you add excess, you're adding a huge excess, which means if you've got more than 2 equivalents, it'll deprotonate the alkyne's proton if it's a terminal alkyne, which means we have to correct for that overshoot by reprotonating it with a weak acid, which is easily done with water. Yeah, that's a good question. So in real life, what you would likely do is this last step, meaning adding water, would be easily accomplished in a separatory funnel. So you just physically dump your crude product in with water, shake it, your organic layer will likely float, and then collect it that way.
But water isn't going to affect that triple bond.
Water will not affect the triple bond, not without other reagents or additives. Yeah, good question. All right, so we've gone through 2 of these. Let's do the next one. The next one, we've got an alkyne going to an alcohol. We can't create an alcohol directly from an alkyne, but we can make an alcohol directly from an alkene, or we can make it from an alkyl halide. Which one do we want to do? Or should we do both? Let's do both. All right, so let's think about it this way. We could have bromine like this. So ignore this one right now. How could we do this transformation going from the right to the left? Think back to last term. Substitution. What would our nucleophile need to be? I'd use a strong nucleophile for SN2, right? So I would use sodium hydroxide, right? Because if you've got your sodium cation and your hydroxide, this will just reach around, do the SN2, kick off your bromine. So that's one option. We've already seen that last term. The other option to make this alcohol would be to make this from an alkene, like this. And what reagent would we need to get the alcohol off of the less substituted carbon? Hydroboration oxidation. So that would be BH3 THF, followed by hydrogen peroxide and sodium hydroxide. All right, so now the question is, how do we get from our alkene to this, or sorry, alkyne to our alkene? Yeah, you could do H2 in Lindlar's catalyst. That would give you a cis alkene. In this case, it doesn't matter. The alkene's not cis or trans. Or, if you wanted, you could do the dissolving metal reduction. Doesn't really matter in this example. You just can't do hydrogenation, though, because you'll overshoot to the alkane. All right? Just to be fun, how would we do this step? Go from our alkene to the alkyl halide in the top right-hand corner. HBr and ROR. Exactly. You need peroxides in there. So as an organic chemist, you could plan out this reaction map and say, all right, we could go to the alkene and then straight to the alcohol, or we could go to the alkene, then to the alkyl halide, then to the alcohol. Which one would you choose? The one with the least amount of steps, right? So in this case, when we ask for the most efficient synthesis, we're usually asking for the one with the fewest number of steps. So I would just erase this and say, yeah, that would work, but who wants to waste that much time on a reaction? It'd be much, much easier to accomplish it this way. Make sense? All right. Next one's a little bit trickier. Provide the mechanism for the following. So I'll give you some time to work on this one, but I'll give you a hint. What sort of functional group do we have in our starting material? It's not just an alcohol. It's an enol. So we've got an enol going on here, and we've got to figure out how we're going to two different ketones. So I'll give you some time to work on this one. All right, just for the sake of time, let's get started with this one. All right, so we've got acid floating around in solution, right? So it's a hydronium ion. The hydronium ion, in this case, can protonate either the alcohol or we could protonate the alkene. The reality is, in solution, both will happen. However, one will take us in a forward progress, or one will take us in a forward direction, the other one won't. Which one do you think is the best one for going forward? The alkene. Okay. So let's just have this alkene steal a proton. Then we would have this alcohol on the left untouched. Will the proton go off of this orange position or off of the green position, do you think? So the proton. Will the proton go to the orange or green site? Well, let's try it, right? So let's determine, is it more likely that we'll have a proton coming off here, or is it more likely that our proton will come off there? Which one's more likely? Left. Why? It's more substituted and resonance. All right. So let's think about resonance. We got these lone pairs here. Resonance stabilization is even more important than it being tertiary, right? So we could go ahead and we can show the resonance structure for this. All right, so we're moving along. We still have water floating around though, right? So we'll account for this water. What do you think will happen in order to get to a neutral intermediate? Yeah, probably just going to have to deprotonate. Okay. So now we're halfway there. We've also regenerated our hydronium ion. So we've got more acid around. So really this will just repeat itself, but with the other alkene. Let me slide all this down. And just like before, we want to get our resonance stabilized carbocation. So this is the best position for that carbocation because then this lone pair can dump down. Now this oxygen has a positive charge. And then what do you think the last step is going to be if water is still floating around? Yeah, deprotonation. So in this last step, water can grab this proton coming off. this up. And we'll get our diketone as our final product. Yeah, if you think about this, right? This sigma bond can rotate. So really you can show this in two different conformations. It could be shown as, whoa, that looks kind of funny. The one on the left or the one on the right. They're the exact same compound. So in this case, this is called acid catalyzed keto enol tautomerization. We started out as an enol. Specifically, we had two enols, and then we tautomerized so that we had two ketones. But really, it's just a lot of proton movement, right? So we're just moving protons around in the overall molecule. Does that make sense? Okay. You're glaring at me right now like there's something wrong. Oh, okay. All right. We've got some more synthesis problems. I will say, historically, for second term organic chemistry, synthesis is where most people struggle. So don't feel alarmed if this is what you're having trouble with. You're not alone in that. I would say for these, pay very careful attention to stereochemistry. Some of these are a little bit more challenging than you might think. All right, just for the sake of time, because we only have 15 minutes left, I'll kind of get us started on some of these. And I'm just going to open up some space in the notes so we can work on this. All right, so if we think about this alkene that we have here, we can make an anti-dihalogenated, or sorry, this alkane, we can make an anti-dihalogenated alkane from an alkene, right? So if we think about it, that main backbone must have been an alkene with an internal carbon-carbon double bond. What reagent do we need? To get two bromines to add across an alkene? Br2. So that will always give you anti-addition, right? Why didn't we worry about an enantiomer here? It's a meso compound, right? It has an internal plane of symmetry after you do a sigma bond rotation. So we don't need to worry about enantiomers. We're only getting one product from this reaction. Now the question is, how can we go from this alkyne to this transalkene? It's only one reagent we have where we can do that. Not H2 and Lindlar's, that gives you cis alkenes. It's the dissolving metal reduction. Yeah, so sodium and then liquid ammonia. So dissolving metal reduction will change that alkyne to an alkene, and halogenation will give you the appropriate product. Make sense? So a two-step reaction, not too bad. All right, now let's try the next one. And the next one, I will give you a hint with. You have to think about sigma bond rotations for the next one. So what I mean by that is, let's consider this product. You can rotate the sigma bond around, right? I'm just going to write plus En down here. And if you rotate that sigma bond, the bromine on the left is still going to be a wedge, but now the one on the right's going to be a dash, right? These are the exact same products. A good way of checking that is the stereochemistry for this carbon is what? It's going to be an R. Stereochemistry for this carbon is what? It would also be an R. Over here, we've got a stereocenter that is an R. And then over here, it's an R. These are exactly the same compounds, but as we saw last term, you can do Newman projections, you can do bond rotations, anything like that with the sigma bond. So now we've got our starting material, or sorry, our final product shown in a different conformation. And our goal is to make this halogenated compound. So then the question is, which alkene do you think we started with? Do you think we started with a transalkene, or do you think we started with a cis alkene? cis, right? Because we need these bromines to be anti to one another, right? If we did the halogenation to the trans alkene, we'd get the product that was shown above, which is not the correct product we want, right? So this would not be the correct alkene we want. We want the cis alkene for this one. And just like we saw before, you can do this with elemental bromine and get the anti-halogenated product, right? All right. So now the question is, how do we get from that alkyne to a cis alkene? H2 and Lindlar's. All right, so those are two similar reactions. However, the main difference is in the top one, we had to go through the trans alkene to get the desired product. The bottom one, we had to go through the cis alkene. So it's subtle but important difference for each of those routes. All right, next one. I already told you, or at least some of you, that there's more than one way to do this one. So let's do it this way. We can make a syn-diol from an alkene, right? What's the reagent we need to go from a alkene or from an alkene to a syn-diol? Everyone's muttering at me. All right, so you can do two. OSO4 followed by NaHSO3, or you can do KMNO4 NaOH, and you have to run this cold. So either of those will give you the syn-diol, but the main thing to remember is the backbone here is staying put, right? We're not changing the zigs and zags at all for this. So we're getting a syn-dihydroxylation. However, just to make things more interesting, let's consider this sigma bond rotation. So I'm going to move this enantiomer down here. So I said that it was a syn-diol, but you could also, if you account for the sigma bond rotation, have an antidiol. If we think about this, we can make an antidiol using what reagents? MCPBA, followed by acid and water, or you can just write that as H3O+. But do you notice this time our backbone is different, right? So our backbone for this looks like it must have originated from a cis alkene. So we could go through either of these intermediates and get to our final product, either cis or trans. It just changes the reagents we need after that, right? So then we can say, all right, we can go from our internal alkyne to a trans alkene by using dissolving metal reduction, which we've already done in the previous example. Or we can go to the cis alkene by using H2 and Lindlar's. Then people will ask me, well, which one's the better route? It kind of depends on the preference and what reagents you have available. I wouldn't say one's necessarily better. They both take 2 steps to get to that final product. Does that make sense? The key thing is students forget about the sigma bond rotation and how to kind of plan backwards to account for those sigma bond rotations. Make sense? All right, we've got one last one. Let me just box this in. This one, we're going from an alkene to a ketone. We saw previously this chapter, we can make ketones by either hydrating an alkyne or by doing ozonolysis. Do you think ozonolysis is likely here? No, we would have a different number of carbons from starting material to product. So it's not likely going to be ozonolysis. But what we could have had was an alkyne that looks like this, right? If we have an alkyne that looks like this, we've got this red carbon that's more substituted, and then we would have this green carbon that's less substituted. In this case, we want the alcohol to add to the red carbon and then tautomerize that to the ketone. So let's actually back this up a little bit. I'm going to slide this down. Say, okay. Whoop. Shoot. Our goal in the first step was to make our enol by hydrating the more substituted side of that alkyne. What reagent do we need to accomplish that? Remember, this is Markovnikov. For alkenes, if you remember, we needed acid and water. We said acid and water doesn't have enough oomph for an alkyne. We had to add in something else. Yeah, HgSO4, mercury 2 sulfate will accomplish that. So in this reaction, you will go through this enol, but then that enol will quickly tautomerize into the ketone, and we just practiced doing that mechanism a few steps ago, right? All right, so now the question is, how can we get from the alkene, our starting material, to that alkyne that we need? We can't do it directly in one shot, so we must have to go through some sort of intermediate. So I'll just put this as a box, and then that intermediate must go to the alkyne. Anybody have an idea? Halogenation. So if you halogenate in your first step, you'll get 2 bromines to add across in an anti-orientation, although it doesn't really matter in this case. You'll get a mixture of enantiomers. And then how do we get to our alkyne? Yeah. Sodium amide in excess, so NaNH2 excess. And then step 2, because it is a terminal alkyne, is to just protonate at the end using a weak acid. Does that make sense? I know these are tricky. Like I said, working in a group not only helps you solve these problems, points out your mistakes, but it just provides a lot of moral support too. So if you ever feel like quitting, you'll have a buddy there to kind of help you out, keep you motivated. So try to do a lot of these in a group. It's very helpful.